Hey everybody, I'm just gonna do a follow-up lesson here, teach you guys a couple of new things when it comes to round elbows. So this is the lesson that I did yesterday, just doing the standard layout using the rise radius here to get our pattern. What I'm going to show you next on the next page is kind of an exploded view of what we see here with the rise radius. So here it is here. So I'm just showing just this little corner. So there's the rise radius, the seam height, and when we divide that circle into equal spaces using the radius, like when we swing that radius and then we go on the center marks or center lines to break that up into equal spaces, they naturally end up at 30, 60, 90. And there's actually a way to calculate these heights without even drawing the rise radius in here. So if I was actually to make a little triangle in here at the 30 degrees, so this is a 30-degree angle here. We have a hypotenuse that stays constant in there, and this height here is actually the height above the seam height here that this line would end up being, right? This 30-degree line, if I was to draw those lines across like normal, it would be at that height on this number 2 line. Number 1 is going to be 0 degrees. Number 2 is going to be at the 30 degrees. Number 3 will be at the 60. And then number 4 would be at the 90-degree height, right? So the 90-degree one is going to be the full height of that rise radius. So, because yesterday we did it where it was 15/16, so this hypotenuse here would be 15/16, and then we're going to be looking for the opposite. So with trigonometry, so TOA, if we're dealing with an angle and opposite and hypotenuse, that's opposite and hypotenuse, so that's going to be a sine function now. So if we actually went sine 30 times 15/16, that'll give us this height here. So sine angle times hypotenuse equals opposite. So sine 30 times 15/16 equals, I'm just going to do this on my calculator. So it's a half an inch. Half inch. So now, rather than drawing out the rise radius here, I could literally just go up to my second line, because I know that's where the 30 degree is, and from the seam height, I can just measure up half an inch, right? Half inch, and then I have that height. Now the next one is going to be this triangle, so hopefully you guys can see that. This hypotenuse still is 15/16, but the angle here now is 60 degrees, right? 60 degrees. And then again, I'm just going to pull the triangle out here so it's a little easier to see. It's just, so I'm, again, 60 degrees, 15/16 hypotenuse, and I'm looking for this height here, the opposite. And that's going to give me the height of this next line here, the next division on my stretch out. So again, it's going to be a sine function. So if I go sine 60 times 15, oops, do that again, sine 60 times 15/16 gives me 13/16. So sine 60 times 15/16 equals 13/16. So now on this next line, I could go from the seam height, measure 13/16, and that would give me the height of my next line. Now, of course, like on a smaller elbow, we wouldn't necessarily do this, but it is a nice way of knowing that this is something you can calculate. It's just as easy on a small elbow just to draw this rise radius like we did before, like on this page here. Just drawing those rise radius on either side and drawing the lines and just doing that over one, up one until you get that pattern. But on a really large diameter elbow, like this is a 7-inch elbow, but if we were doing like a 40-inch elbow, 12 divisions is not enough. You know, because the stretch out on a, like, let's go 40 times pi, you know, that's 126 inches almost. So if I had 12 equal sections on 126 inches, each one of these divisions here would end up being like 10.5 inches apart. So having just these 12 points, 10.5 inches a point, it's not going to be a very smooth curve on there. Or it's going to end up being with lots of big flat spots, and it's not going to translate well and fit together very well. So on a really large diameter elbow, it's better to actually break this whole stretch out into quadrants. So have 4 equal spaces, because this little rise radius, if I show you here again, right, this quadrant or quarter of a circle covers the first 4 points. This quadrant here would cover the next 4 points. It would be, if I drew the full circle in here, this quadrant here would deal with the first 4 points. This one would deal with the next 4 points because they're all above the seam height. And then this one is going to do the next 4 points, and this one will do the last 4 points because they're going to be on the bottom, right? Hopefully I can show you here. So like this is the first quadrant. So if I had the full circle here, these points, because they're the same as these points, so I don't have to draw the full circle, but these 4 points here are going to take care of those first 4. Then these ones here are going to take care of these next 4 in that quadrant. These ones here are going to take care of these next 4 right to that quadrant. And then the last corner of the circle takes care of the last quadrant, right? So we're essentially going to do that with a large scale elbow, so like a 40-inch elbow. But rather than having just these 4 or dividing a circle into 12 equal spaces, what I'm going to do is take one of these quadrants and divide it into 10 equal sections, right? So if I took the rise radius again, seam height, rise radius, and I took this first 90-degree bend and made it into 10 equal sections. So that means there's 90 degrees divided by 10, means each one of these increments goes up by 9 degrees, right? 9, 18, 27, 36, 45, etc. And then it's going to be the same thing. I'm gonna do just little triangles to find out the little heights here. So the first one is going to be sine 9 degrees times whatever the rise radius is. On a 40-inch elbow, I don't know, let's just say that it's 2.5 inches. I'm not sure if that's what it would be. Like, it depends on how many pieces it is, but I'm just going to use that as an arbitrary length. So on every one of these dimensions here, it's going to be sine whatever angle you're using and then so whatever angle times 2.5 inches, and that's going to give you the opposite, right? And so it's going to give you how much it's rising. So this first one here, sine 9 degrees times 2.5 inches is going to give me this first height here. So it's going to be right there. And then sine 18 times 2.5 inches is going to give me this next height here above the seam height. Sine 27 times 2.5 gives me this measurement here, how much I have to go above, right? And then I'm just going to keep going along. And it's going to bring me all the way up, all these little increments, all the way until I hit this point right here. So that'll be that first quadrant of my pattern by doing these numbers here. Now I don't have to redo them every time because whatever I rose up here, I'm just gonna have to go backwards then for the next 10 degrees, right? Or the next 10 increments. So I started off going from 9 up to 90. Then I would basically go from 90, 81 degrees, 72 degrees, 63 degrees, etc. until I'm back down to 0. And then I'd end up doing below this seam height line. So I'd end up getting the same pattern, but just on, I'll end up with this pattern again. But, rather than 4 increments, there's going to be 10 in there. So I'll get up to the highest point, down back to the seam height, and then to the lowest point, and then back up to the seam height again. So anyway, hopefully that makes sense. It's just fairly simple trigonometry. Just remember that we're using a hypotenuse here because this is an arc that we have a length of, and it doesn't change anywhere, so that it always ends up being the hypotenuse of the triangle, and we're just trying to find out how much it rises off this baseline. All right, if you have any questions with that, just give me a call or an email, and hopefully I can answer it for you.